Okay, very good morning, guys. Today we are going to see about introduction about 8086 microprocessor, right? So in the previous classes in your module 3, this is only a single line as per your syllabus, but you can expect any kind of questions from 8086 because that is introduction to 8086. So they can ask anything from that. So this portion also you have to study like what you have done in your 8085. Okay. So that is what is 8086. So 8086, it is nothing but it is same like an 8085 microprocessor, but it has some additional advantages compared to 8085. It has some additional advantages. That is nothing but it's an extended version of your. It is an enhanced version or extended version of your 8085 only, and it is actually designed by Intel. That is in 1976. Okay. Then another feature, the main feature here it is a 16-bit microprocessor and it has 20 address lines and 16 data lines. But you can know you know that what about your 8085? What about is this an 8-bit or a 16-bit? Okay, you have to verify. You have to differentiate like that. What is the difference between in the case of data bit size? Then how many address lines will be there and how many data lines will be there. Okay, so all these things will be different from your 8085. Then it is a same like your 8085. This one is also having a powerful instruction set, and actually in the 8085 the most common operations are addition and subtraction only. But multiplication and division you can easily carry out in this 8086. That is one of the additional advantage of this 8086. And then the modes of operation, all those things we will see later. But as an introduction, what you can tell it as that there is two. It will support a maximum mode as well as minimum mode. Maximum mode is nothing but if you are using multiple processors together, it will be in the maximum mode. If it has only a single processor, you can call it as a minimum mode of operation. Okay, this is what is just an introduction about your 8086. Now we will see the features of 8086. So there are so many features are there for 8086. The first thing is it has an instruction queue which is capable of storing 6 instruction bytes from the memory, resulting in faster processing. So compared to 8085, what is happening here? 8085 it will hold only 1 byte of data. Okay, it will hold only 1 byte of data. That is just a 8 bit address. 8 bit location will be given for this storing the data. So but in the case of 8086, it can fetch more data from the memory, that is maximum of 6 instruction bytes. So 6 instruction bytes means totally 6 into 8. So 36 bits can store at a time. So what is happening? So every time it can store a 6 byte of data. So after the 6 byte of data only the memory, the address location has to go there and fetch the data from the memory. Okay. So that is what is the advantage of this one. It will provide a faster processing when it is compared to 8085. Then another thing is we have already seen that it is a 16-bit processor having 16-bit ALU, 16-bit registers, internal database, and 16-bit external database. But in the case of 8085, everything was 8-bit only. Okay, you have 8-bit database, all the registers were 8-bit because the processor is an 8-bit processor only. Okay, so everything was 8-bit only in the case of 8085. Uh, so then next point is there are three variations. So three variations are available here for 8086. They are 5 megahertz based on the clock frequency. Based on the clock frequency, there are three variations are available. First one is normal 8086 where the clock frequency is 5 megahertz. Then 8086-2, this is 8 megahertz. And the last one is 80861, this is 10 megahertz. So these three variations are available for 8086. Then two stages of pipelining is there. Pipelining and all we will see later what is pipelining. Then they are test stage and execute stage which improves the performance. So test stage means It can pre-fetch up to six. So fetch means you are getting data from the memory. Okay, because it can hold a 6 byte of data. So at a fetch cycle, it can take 6 byte of data at the same time. But in the case of 8085, what will be there? You can take only 1 byte of data. That is difference between 8085 and 8086. That is nothing but your fetch stage. Execute stage is nothing but the processor is executing the instructions. Then what about interrupts? There are 256 vectored interrupts are there. Okay, and it consists of 29,000 transistors. So if you are writing this dem examinations, sorry, microprocessor, if you are writing all the competitive examinations, so these type of points you should be remember. How many interrupts will be there in 8086, then how many number of transistors. These type of questions you can expect in your competitive examination. So you have to remember all these numbers. Okay. So this is 256 vectored interrupts are there. So we will see the interrupts later. So that time we will study thoroughly about what is the interrupts. So there are hardware interrupts, software interrupts. So there are different types of interrupts are there. So we will see each one by one. Okay. So these are the features. So the main features are it can store 6 instruction bytes. That is the first point. Then second point, it is a 16-bit processor. So all the data, all the communications available with this processor, they are 16-bit only. Okay, 16-bit ALU, 16-bit data bus, 16-bit registers. So everything is 16-bit. Then next point is it is three versions are available based on the frequency of operation. So there are 5 megahertz, 8 megahertz, and 10 megahertz. These are the frequencies which are available with 8086. Then next one is pipelining. Pipelining is it has two stages. First one is fetch stage and second one is execute stage. So fetch stage, what will happen? It will pre-fetch 6 bytes of instructions from the memory, right? That is the advantage of 8086. And execute stage, so the instruction which is there in it is now stored in your registers, right? So then it will execute those instructions. That is what is the execute stage. Then we were talked about the interrupts. So there are totally 256 vectored interrupts are there in the 8086 processor. Then total number of transistors are there is 29,000 transistors are there in the 8086 processor. Alright. Now what we are going to see is we will see the difference between 8085 and 8086. So this is also you have to be remember. The size is 8085 is an 8-bit processor that you know. 8086 is a 16-bit processor. And the address bus 85 will only 16 bits are there, right? 16 bits. So out of that 16 bits, 0 to A0 to A16. So A0 to A16, out of that A0 to A7, you can consider it as a both as data bus as well as address bus. Then A8 to A15, it will be completely as the address bus only, right? That's what we have seen in 8085. So there are 16-bit address in 8085 and 20-bit address bus in the 8086. Memory, 85 can access up to 64 KB memory. That also we have seen in the last class, right? Memory fetching, memory address decoding. That time we have seen the access up to 64 kilobytes, but 86 can access up to 1 MB. Okay, 85 is up to 64 KB and then 86 it is up to 1 MB. Then instruction 85 doesn't have an instruction queue, right? Because why it doesn't have an instruction queue? Because whatever the instruction you want to execute, you are bringing the instruction from the memory and you are executing in the 8085 case. But in the case of 86, you are having you can have 6 bytes of instruction at a time. Okay, you can have 6 bytes of instructions at a time. So definitely it is requiring an instruction queue. So one after one, okay, like that only the instruction will be executed. So once the complete is over, then only the next fetch cycle will happen, and it will fetch the data from the memory after the instruction is over. Okay, so 85 doesn't have an instruction queue, but your 8086 has an instruction queue. Next one is pipelining. 85, we didn't see anything about pipeline, but in the case of 86, it supports the pipeline architecture. That also we will see later. What is the pipeline? Then input output access. So 85, it can access at 2 raised to 8, 2 raised to 8, that is 256. Because your database is 8-bit database only in the 8085. So it can access 2 raised to 8, that is equal to 256 input output devices at a time. But in the case of 8086, this is a 16-bit, right? So 2 raised to 16, that is equal to 65,536. So these numbers also you have to be remember. Okay, these numbers also you have to be remember. So 8085, it is up to 2 raised to 8, that is 256 input output devices. But in the case of 8086, because this is a 16-bit, right? 85 is an 8-bit, so 2 raised to 8. So this is a 16-bit processor. So that is 2 raised to 16, that is equal to 65,536 input output devices. Cost 85 is low because it doesn't have, it is not an advanced one. Okay. And 86 have some advanced features. So definitely your cost of the 86 is higher than 85. Okay. So this is what is the comparison between 85 and 86. So the comparison, the parameters of comparison are size, address bus, memory, instruction, pipelining, input output, and cost. So you have to compare. 85 is a 8-bit, 86 is a 16-bit microprocessor. Address bus 85 is 16-bit, 86 is 20-bit. Memory 85 is 64 KB and 86 is 1 MB. Instruction 85 doesn't have an instruction queue, but 86 has an instruction queue. Pipelining will support only for 86. Then input output is 2 raised to 8 for 85, 2 raised to 16 for 86. Then cost, definitely cost of 86 is high because that is the most advanced one. Okay. Now next is we are going to see the architecture of 8086. You may copy down this architecture and once you complete, let me know. Did you finish?
Guys, if we have completed, let us know so that we can proceed further. Are we done? Madam, it seems they have completed. There is a response on the feedback, so we can proceed.
Okay, okay, sir. So the next point is architecture of 8086. Uh, so here the architecture, actually there are two units will be there. First one is BIU and second one is EU. Okay. So BIU is bus interface unit and EU is execution unit. So the total architecture is divided into two categories, two parts. First one is BIU, that is bus interface unit, and second one is EU, that is execution unit. Okay. So this is the differentiating line. So this part is completely bus interface unit and this part is completely execution unit. So we'll see one by one. So 8086 microprocessor is divided into two units. First one is execution unit and second one is BIU. So first we will see about the execution unit. Okay, this part we will see first, then we will see about the bus interface unit. So execution unit gives instructions to BIU stating from where to fetch the data and then decode and execute those instructions. Okay. So, and also its function is to control operations on data using the instruction decoder and ALU. So, execution unit. So, this portion holds the complete control of the system. This execution unit, it holds the complete control of the system, right? So, this execution unit will tell the BIU that from where it has to take the data, either from memory or from the input output devices. So it will give instruction to the BIU, that is bus interfacing unit. It will give instructions to BIU that from where you have to take the data. Okay, that so execution unit is the head. Okay, that is the brain. So it will tell the system BIU that from where you have to take the data. So those data, it is either from memory or from input output devices, and also it has to take the data as well as it has to execute the data of operation. That is what is execution unit is doing, and it doesn't have any direct connection with the system buses as shown in the above figure. It performs operations over data through BIU. Okay, so these are the 2 points. This is gives the complete control, and it will tell the BIU from where you have to take the data and you have to execute the data. So once you are executing, you can transfer the data either to memory or input output devices, whatever it is. So all these functions will be carried out by BIU only, but the instruction for doing that is given by execution unit. Okay, so the execution unit, that is the brain here. So that is the brain of the system. So it will give the instruction And also it doesn't have any communication with the peripheral devices. It cannot communicate with the peripheral devices. It can communicate only through the bus interface unit. Only this unit is doing the communication with peripheral as well as memory unit. Only EU will provide the information or the instruction to the BIU to do what. So then we will see each and every part of the EU. First one is ALU. ALU is arithmetic and logical operations. All these things carried out in ALU, that is plus, minus, multiplication, division, or and not operation. All these functions are carried out in the ALU, that you already know. Then next one is most important thing is flag register. So here flag register is a 16-bit flag register are there. But in the case of 8085, it was only 8-bit flag register. So there are two groups of flags. First one is conditional flag and second one is the control flag. So we will see each one in detail. So conditional flag means the result of the last arithmetic or logical operation executed in the ALU. Okay, it represents the result of last arithmetic or logical instruction executed in the ALU. So the conditional flags are of totally 6 types. First one is carry flag, auxiliary flag, parity flag, zero flag, sign flag, and overflow flag. Okay. First we'll see auxiliary is nothing but auxiliary carry only. Auxiliary carry flag and auxiliary carry flag. Carry flag is this flag indicates an overflow condition for the arithmetic. So if you are adding two binary numbers, so the result is you are having a carry is there. Okay, suppose you are adding triple one plus 11100, sorry, 111. Suppose if you are adding like that, if you are considering the MSB bit, if there is a carry is there, then the carry flag will set. That is the carry flag. Auxiliary carry flag means if there is a carry in from D0 to D3. So you consider if it is a 8-bit data, you are considering if it is an 8-bit data, what is happening? First 4-bit you can call it as a lower nibble, and upper nibble means last 4 bits are upper nibble. Okay, D0 to D3 is lower nibble, D4 to D7 you can call it as a upper nibble, right? So if D7 is having a carry, so carry flag will be set. Okay, set as 1. If D3 is having a carry, then auxiliary flag will be set. I hope you understood what is the difference between carry flag and auxiliary carry flag. If so, can you post a message? You understood or not? Difference between carry flag as well as the auxiliary carry flag?
That is a response, madam. We can proceed. So they understood. Section C.
Okay, okay, fine, okay.
Section C. Just let us know if you understood the difference between those two things. As far as response from A and B, okay. I suppose Saranya is the only person in the section C, I suppose. What happened to others? Sedu, Manoj, Praveen, Sabari? Are you guys there, first of all? Right? Guys, are you there? The names which I have said, right? Surya, Swati, Tarun, Yuvan, Varshika, Alani, Nalasivam. Yes, ma'am. Yes. Guys, C-section. Yeah, Sarada has come for the rescue. Thank you, Sarada. Madam, we can proceed.
Okay, sir. Okay. Uh, so, so carry flag and auxiliary carry flag. Carry flag means if there is a carry in the D7 bit, that is carry flag. Auxiliary carry means if you have a carry in the T3 bit, that is auxiliary carry flag. Okay. Then next one is parity flag. Parity, anyway, you have studied about even parity and odd parity in the case of your digital electronics, right? So same way only here. The result is having even number of ones, then the flag parity flag is set as one. Okay, if the parity flag is one, it has the meaning that your result. Okay, after the arithmetic operation only, the flag is going to set or reset, right? So after the arithmetic operation, the result is having even number of ones. That is the meaning your parity flag is set as one, and the odd number of one, it with the parity flag is set as zero. The next one is zero flag. Then what is zero flag? Zero flag is set to one when the arithmetic or logical operation, your result is zero. If your result is zero, zero flag will set as one. Then next one is sign flag. Sign flag means it will hold the sign of the result. Okay, when the result is operation is negative, then the sign flag is set as one. So if the sign flag answer is one, if the bit in the sign flag is one, it means that your answer is a negative answer. Next one is overflow flag. If it exceeds your system capacity, okay, if it is more than a 16-bit data, if it is more than 16-bit data, suppose if it is an 8-bit data, if the answer is more than 8-bit data, the overflow flag is set as one. So it will tell that it is beyond the system capacity. Okay, I hope you understood what is conditional flag. Conditional flags are carry flag, auxiliary carry, parity, zero, sign, overflow. Okay, so you have to remember in this order. Carry and auxiliary carry is if your result is having carry in D7 bit, that is carry flag will set. If there is a carry in your D3 bit, your auxiliary carry flag will be set, right? Then parity flag means if the result is having even number of ones, parity flag is equal to 1. If the result is having odd number of ones, the parity flag will be 0. Zero flag means if the resultant answer is 0, then zero flag will be set. Then sign flag means what is sign flag? If the operation is the result is negative, then sign flag is set as 1. Right? Overflow flag. If the result exceeds the system capacity, then overflow flag will be set as 1. So these are the conditional flags. Now what we are going to see is control flag. Okay, so there are two types, but in the case of 8085, you have studied only conditional flags, right? You might not have studied about the control flags. So the control flags are there in your 8080. Control flag, what is control flag? It is control the operation of the execution unit. So this is what is the control flag will do. And here conditional flag, it is based on the result of ALU. Okay, what is the result there in the ALU? That is conditional flag will set. And control flag, it will control the operation of the complete execution unit. So there are three are there. They are trap flag, interrupt flag, and direction flag. Trap flag means it is used for single step control and allows the user to execute one instruction at a time for debugging. If it is set, then the program can be run in a single step mode. So single step mode actually we have seen in your laboratory session. Okay, so you have to execute one instruction at a time. That is trap flag. We have to execute one instruction at a time. That is single step mode. So if trap flag is 1, it will execute only one instruction at a time. That is trap flag. Then interrupt flag is this one also you can enable or disable. So used to allow or prohibit. If it is enabled, it will allow in an interrupt, and if it is disabled, you cannot access an interrupt. Okay, or external unit. External unit communication only through the interrupt, right? So if it is enabled only, it can access an external unit. If it is disabled, you cannot access an external unit, or an interrupt cannot be given to the system. Next one is direction flag. So the direction flag is used for the string operation. As the name suggests, when it is set, then the string bytes are accessed from the higher memory address to the lower memory address and vice versa. That is direction flag. So whether it has to access from higher memory address to lower memory address, and if it is reset, if it is 0, you can access from lower memory address to the higher memory address. That is direction flag. So these are the control flags. First one is trap flag, second one is interrupt flag, and third one is direction flag. Okay. I hope you might be knowing, you understood about the flags. So flags are conditional flag as well as control flag. Conditional flag, there are 6 types: carry, auxiliary carry, parity, zero flag, sign, and overflow. In the case of control flags, there are 3 types: trap, interrupt, and direction. I hope you understand about the flags, right? Then now what we are going to see is, we are going to see about the general purpose register. So here the general purpose registers are, these are the general purpose registers. Okay. AX, It is combinedly, you can call it as AX. Okay. AX is a 16-bit register, and AH is an 8-bit, AL is another 8-bit. Then this is BX. Okay, BX is divided into 2, like BH and BL. Then CX is divided into CH and CL, and DX is divided into DH and DL. So these are the general purpose registers. So ABCD. Okay, you can remember like that, ABCD. So ABCD is AX, BX, CX, and DX. So this is what is 8 general purpose registers, that is AHAL, BHBL, CHCL, DH, and DL. So this is, it can be stored 6-bit of data. Suppose if you want to store 16-bit data, you are clubbed together, that is AHAL as AX, right? Then DHBL as DX, CHCL as DX, and DHDL as DX. This is what is the general purpose register. So we'll see what is AX, BX, CX, and DX register. So what is AX register? It is known as accumulator register. It is used to store operands for arithmetic operations. Okay. So move AX, BX, like that. So some instructions will be there. So that time it can hold the operand. Okay. It can hold the operand for the arithmetic operation. That is AX register. Also you can call it as an accumulator register. Okay, so this accumulator you can represent it as an AX register. Then base register is BX register. Base register is BX register. It is used to store the starting base address of the memory area within the data segment, right? Then CX register, it is used as a counter. Okay, counter CX register. It is used in loop instruction to store the loop counter. So that also things will come into picture when you are writing a program. Okay, that time only all these things will be come into picture. That is CX register. Then DX register. DX is used to hold input-output port address for input-output instruction. So DX is used for the input-output communication. Right. If you are doing a program, if you want to access an input-output devices, that time you are using this DX register. In the case of counters, we are using CX register. For base register, you are using DX register. Usually in the program, if it's a general program, it doesn't have any counters or input-output ports, you are usually using AX register as well as DX register, because all the arithmetic operations will be have to be done using AX register. So normal process, if you are writing a program for addition, subtraction, multiplication, division, and all those cases, you are using AX register and DX registers only, right? So these are the general purpose registers. So the general purpose registers are AX, BX, CX, and DX. AX is accumulator, BX is base register, CX is the counter register, and DX is holding the data for input output port. Okay, called the input output port address. So these are the general purpose registers. And the last one is stack pointer. Stack pointer is nothing but stack pointer, the same as that is what is there in your 8085. Only difference is here it is a 16-bit stack pointer, stack register is there. But in the case of 8085, it was only 8-bit register. Here it is 16-bit register. That is the difference between stack pointer in register in both 8085 and 8086. And the last one is bus interface unit. So bus interface unit, it takes care of all data and addresses transfers on the bus for the execution unit, like sending address, fetching instructions from the memory, reading data from the ports and memory, as well as writing data to the ports and the memory. So EU has no directive connection with the system buses, so this is possible with the BIU. EU and BIU are connected with the internal bus. So whatever instructions is given by execution unit, that is executed by the bus interface unit only. So if you want to read a data from memory or input output device, or if you want to write a data to memory or input output devices, all those things will be carried out by bus interface unit only. Okay, so that is what is a bus interface unit. So here these are the points with the parts of bus interface register. They are instruction queue, then segment register, then instruction point. Okay, these are the things. Instruction queue also we have seen already, because it can handle 6 bytes of data at a time. Okay, 6 bytes of next instructions it can store, right? So that is what is instruction queue will do. Okay, there you get up to 6 bytes of next instruction and stores them in instruction queue. When execution unit execute instruction and is ready for its next instruction, then it simply read the instruction from the instruction queue, resulting in increased execution speed. Because it doesn't need to every time go to memory or input output devices to fetch the data. It doesn't need to like that. It can store 6 bytes of data at a time, right? So one is executed only, next is only from the instruction queue, it has to take the data and it has to execute, right? That is the instruction queue will do. Fetching the next instruction while the current instruction execute is called the pipeline. In the case of 8085, so once the data executed, then only it will move to the memory or input output device to fetch the next instruction, right? But in the case of 8086, while executing one instruction, the device can, or 80 processor can access the next instruction. So that is known as the pipelining. Okay, so that is so that we have seen it can handle two properties at a time. First one is fetching and executing. So both can be do at a time in the case of 8086. But in the case of 85, you can do one task at a time. Either you have to fetch the data, then you have to execute. Once the execution is over, again it go to fetch the data, then it has to execute. So it will take more time. Okay, it will take more time. So that is the problem with 8085. So this is that problem can be avoided using pipelining technique in your 8086. Next we are going to see about the segment registers. The segment registers are CS, DS, SS, and ES. So we will see the registers in detail. So this segment registers, it holds the address of instruction and data in memory, which are used by the processor to access memory location. And it also contains one pointer register IP, which holds the address of the next instruction to executed by the execution unit. So CS is, you can call it as a code segment, and it is used for addressing a memory location in the code segment of the memory where the executable program is stored, right? CS is the code segment, so you have to keep in mind that this is code segment, DS is data segment, S is stack segment, ES is extra segment. Okay, So code segment, what is the use of code segment is, it is used for addressing a memory location in the code segment of the memory, whereas the executable program is stored. Data segment is data used by the program and is accessed in the data segment by an offset address or the content of other register that holds the offset address. So all those things we will see in detail in your addressing notes, right? Then SS is nothing but the stack segment, stack the same as your stack registers. Then ES is extra segment. It is used by the string to hold the extra destination data. So these are the segment registers. So data, so code segment, data segment, stack segment, and the extra segment. And the last point is instruction pointer. So this is a 16-bit register used to hold the address of the next instruction to be executed. That is what is an instruction pointer, right? So these are the main parts of an architecture of an 8086. I hope you understood. If you have any doubt, please clarify now. Understood or not?
Yes, madam, you can proceed. I think there are responses in the other chat. We'll proceed.
Okay, guys, thank you. Next one is the pin diagram, 8086 pin diagram. You may draw the pin diagram and we will resume it after 5 minutes. Shall we proceed?
Yes, madam. We will.
Okay, sir. So this is the pin diagram of 80836 IC. This one is also a 40 pin IC, but here there is some difference between 8085. Uh, Ground, there are two ground pins, 1 and 20 are ground pins, and 40 is VCC, right? Then totally 20 address lines are there, right? So A0 to AD4, 14 here, then 15 to 90, okay, A0 to A90. Out of that, A0 to A15, it can be accessed as both the data as well as address line. Okay. AC, that's why it is named as AD0 up to AD15. So this AD0 to AD15, it can be worked as both address as well as data lines. That's why it is given AD0 to AD15. Right. And A16 to A19, this is only for the address, only for sending address, because this is a 20-bit address. So it can only for sending address. Next, then NMI, INTR, these are interrupts. NMI is a non-maskable interrupt. INTR is interrupt signal, INTR. So these two are external hardware interrupts. Then clock is the clock frequency, right? Based on the external clock pulses, you can give a clock pulses. So we have seen 5 megahertz, 8 and 10 megahertz, right? Then ready and reset signal. This is also for communicating with the other devices. Then here hold acknowledgement. So these things we will see. Okay, we will see. Then WR memory. This is M bar IO is write is this is write signal. Hold and hold acknowledgement for while communicating with the external devices. WR bar is write. M bar IO is memory or input output. Then DT bar H bar, so that also we will see. DEN is data enabled, ALE is address latch enabled, INTA is interrupt acknowledgement. Then what is MN bar, MX bar, that is minimum or maximum mode. Then RD is read signal, BHC is the best enabled. Okay, so these are the things. So we will see each and everything in detail. So this is first one is power supply as well as frequency signal. You are giving 5-volt DC supply to VCC pin and uses ground at the VSS pin 1 and 20 for its operation. One is used for ground and 5-volt DC you are given to the VCC pin. The clock signal 5 megahertz, 8 megahertz, 10 megahertz. That already we have seen in the features of the 8086. Address bus and data bus, these are 16-bit address or data bus, that is AD0 to AD7, which carries lower order byte data, and AD8 to AD15 carries higher order byte data. So during the first clock cycle, it carries 6-bit address, and after that it carries 16-bit data, right? So that also we have seen. Then address or status bus, that is A16 to A90, A16 to A90. Okay, A16 to A19 is address or status. S3 to S6. These are the status buses. So there are 4 lines are there. During the first clock cycle, it carries 4-bit address, and later it carries status signal. Okay. Next one is BHE is bus high enabled. BHE is bus high enabled. It is available at the pin number 34 and using data bus D8 to D15. Transfer of data. If the BHE signal is high, then only you can transfer the data through ADI to AD50. Okay, that is address high enabled. So higher address, that is D8 to D50. That is the second half. D8 to D50. If it is enabled, then only you can transfer the data through a D8 to D50. And this signal is low during the first clock cycle. Thereafter, it is activated. Then read operation. Similarly, write signal is you can call it as a write operation. Ready means acknowledgement signal from input output device that data is transferred. So uh, what to tell about the input output devices? So you are transferring data to the input output devices, right? So what you have to do is make your input output devices is telling to the system that I am ready to accept the data. Okay, input output device also has to tell the your processor. Okay, without telling that you cannot send the data. So input output device is telling your system that I am ready to accept the data, right? That is ready signal. So if the ready signal is high, the system knows that that particular input output device is ready to accept the data. Okay, so that is ready signal. Then reset signal means after the execution, you have to reset the microprocessor. Again, you have to start a new instruction. Okay, so that is reset signal. INTR is nothing but an interrupt signal, interrupt request signal. Some other devices, if you want to do an interrupt, okay, it needs to interrupt the signal, interrupt the microprocessor, stating that I want to transfer the data. One external device is telling that I want to transfer the data, like that the external devices is telling your system, right? That is INTR. NMI is non-maskable interrupt. So if you want to communicate some input output devices with your system processor, you are using through NMI, because once it is enabled through NMI, it will definitely execute that particular program. Then only it will do all other programs. That is NMI. Then test signal is it is wait state. When the signal is high, the processor has to wait for idle state, else the execution continues. So if a test signal is high, means if it is high, the processor has to wait for some time. Okay, if the processor has to wait for some time. It has to be in idle condition. It do not do any work. Then what to do? Otherwise, if it is zero, what it can execute, it can work as usual. It can execute the execution. What is the program where there? It can continue that. Then MN bar, MX bar, that is minimum and the maximum mode of operation. Hold acknowledgement. This is hold means so the signal indicates to the processor that the external device are requesting to access the address or data bus. Because suppose if you are using multiple processors, okay, this is not only a single processor, multiple processors or multiple input output devices will be there. So what it is doing, the multiple devices, the input output devices are requesting processor, I want to use your input output data bus. Okay, input output or address or data bus. I want to use your address or data bus. The input output device is requesting the processor that I want to I want to use access your input address or data bus. Then XLDA means it will tell the processor if the XLDA signal is high, it is telling the output devices stating that okay, you can use it. That is what XLDA signal means. Okay, you can use it. If it is accepting, XLDA signal will be high. So you can use the address or data bus. That is what is called XLDA and hold signal. Then QS1 and the QS0. So there are some conditions. If QS0 is 0, both are 0, 0, there is no operation in the processor. If it is 0, 1, first byte of opcode from the queue. If it is 1, 0, you have to empty the instruction queue. Okay, this is about the instruction queue. You have to empty the queue. Then 1, 1, subsequent bytes from the queue. Once it is taking the first byte, then it is using the second byte, then third byte, fourth byte, like that. Totally 6 bytes are there, right? 6 byte instructions are there, right? So it will execute the one byte after another one. Okay, so that is QS1 and QS0. Then S2, S1, S0 is nothing but the status signal. Uh, if all these things are zero, interrupt acknowledgement, 001 input output read, 010 input output write, 011 this is halt signal, this is halt signal, 100 opcode fetch, 101 memory reader, 110 memory write, and a triple one this is passive command. Okay, so these are QS1, QS0, and the S1, S2, S1, S0 also. So S2, S1, S0, these are the status signal only, which is it is used to bus controller to generate the memory or input output control signal. And the next one is lock. Lock RQGT1 and RQGT0. These only are printing here. So lock means when the signal is active, it indicates to the other processors not to ask the CPU to leave the system bus. It is activated using the lock prefix on any instruction and is available at pin number 29. So lock means if it is activated, uh, no other devices can ask the CPU to use to leave the system bus, because if the CPU is working on the system bus, it has to be continued, because no other device can be asked to the CPU. I need to use it. Okay, it cannot ask like that. So that is the lock is doing. So if the lock is high, no other device can access the system bus, or other processors not to ask CPU to leave the system bus. Once CPU leaves the system bus, then only other devices can access it. So it cannot access, it cannot. So that means here you have seen about hold, no? So once the low signal is high, hold will not be work. Hold means it is asking the CPU, I need to use your data bus or address bus. Okay. But if lock is high, it cannot give the hold command. It cannot give the hold command. It cannot ask the system or the CPU to leave the system bus. Okay. That is what is lock. Next one is RQ bar GT1 and RQ bar GT0. This is request and grant signal used by the other processors requesting the CPU to release the system bus. Okay. If lock is high, it cannot access these commands. Okay. And if it is low, then only you can access RQ bar GT1 and RQ bar GT0. That is request and grant. So request, there are two things are there. So if you are requesting the CPU that I need to use the system bus, that is requesting. And if the CPU is accepting that, then it will be granted. Okay, it is granted that you can give the you can use the system bus. So this one is having the highest priority than GT1. Okay, RQ bar GT0 is having the highest priority than GT0. Suppose if you are using one process in GT0 and then second processor in GT1, it will first consider the GT0. What is there in your GT0, that only it will first consider. Right. So this is what is the your pin explanation, pin diagram explanation. I hope you all understand that. Any doubt regarding this in the pin diagram? Is that okay? Are you guys there or not?
Madam, there are responses in the chat box.
Sir?
There are responses in the chat box.
Yeah. So actually only Sharanya and Sharada is responding from C section. And Arunita, Sudarshan, Gayatri, Pratisha. Only these guys are there in A and B section. No one from B section, all from A only. What happened to B section?
Shaktivel and Ritish will now join.
You understood or not? Shall we move?
We'll proceed, madam. There is a response from B section. Thank you, Ritika.
Okay. So instruction set we will see later. Now we will finish up to interrupts. Okay. So what are the interrupts there in 8086? So interrupts here actually there are two types. First one is hardware interrupt. Second one is software interrupt. So interrupt. What is the definition of an interrupt? So it is a method of creating a temporary halt during program execution and allow peripheral devices to access the microprocessor. Okay, that is what is interrupt. Okay, so while executing your processor is executing a main program. Okay, suppose if you are giving an instruction, it is executing a main program. So while executing, some external, it is not necessary to be external, it can be internal also. Okay, so some uh, distractions will happen. Okay, it asks the processor to stop what you are executing and you have to execute my program. Okay, that is what is the interrupt is doing. Okay, so interrupt is a method of creating a temporary halt during program execution and allows peripheral devices to access the microprocessor. This is what is the interrupt. So next one is the most important thing, that is interrupt service routine. Interrupt service routine responds to that interrupt with an ISR, which is a short program to instruct the microprocessor on how to handle the interrupt. Okay, ISR is nothing but it is a small program to instruct the microprocessor on how to handle the interrupt. This is what is ISR. Okay. So ISR is a common question in your examination. It is a 2-mark question. Define ISR, interrupt service routine. Define ISR. This is a 2-mark question you can expect in your um, questions. Okay. In the 2-mark question, ISR, what is interrupt? What is ISR? So it is not necessary. If you have studied in 8085 also, so this is common to all. Okay, so this is not because if you are this is in 8086 you are studying. It is common to all type of microprocessor or microcontroller. Okay, so you cannot categorize that it is under 8086. You cannot do like that because it is common to all. So you have to study the definition. So ISR, which is nothing but a short program that is instruction to the microprocessor on how to handle the interrupt. So there are two types of interrupts. First one is hardware interrupt and the second one is software interrupt. There are two hardware interrupts are there in 8086. They are NMI and INTR. So you have seen the two pins there, right? In NMI and INTR. These are the two pins are used for the hardware interrupt, NMI and INTR. So what is NMI? NMI is nothing but a non-maskable interrupt. INTR is a maskable interrupt. So what do you mean by non-maskable? So once the NMI through a device is accessed through NMI, the whatever program is executed by the microprocessor has to give a stop. It is not a complete stop, a temporary stop. A temporary stop to the program what is executed during that time. Immediately it will go to the program which is given by the NMI pin. Okay, that is non-maskable. So whenever it comes, microprocessor has to do the NMI task. Okay, it cannot continue. You hold, you be there for some time. You be there for some time. Then I will do it later. You cannot tell like that. Okay, so that is what is NMI. That is non-maskable interrupt. Right. Then what is INTR? It is maskable interrupt. So whenever the processor needs to take, then only it will take the INTR. So it is not necessary to be immediately it has to halt the program what it was executing and then it has to work it on that. So it is nothing like that. So NMI is like what to say? NMI is nothing but it is a non-maskable. So whenever it comes through NMI, it has to work it on that. That is NMI. Then INTR is maskable. So you can hold for some time and it can be accessed. Okay, it can be isolator accessed also, not a problem. That is maskable interrupt. So there are actually you need to study all those things. But only thing is you have to be there. What is NMI? That is a non-maskable interrupt. It has the highest priority. NMI has the highest priority because this is a non-maskable, right? It has the highest priority, and you can also call it as this is a type 2 interrupt. NMI is a type 2 interrupt. So those types we will see there. Then INTR is a maskable interrupt because the microprocessor will be interrupted only if interrupts are enabled using set interrupt flag instruction. It should not be enabled using clear interrupt flag instruction. Right? That is INTR. It is a maskable interrupt. So whenever it is required, then only you can utilize the INTR. Whatever data is there in the INTR field, it can utilize the INTR. Okay. That is maskable interrupt. NMI is whenever NMI comes, it has to work it on the NMI. Okay, it cannot hold any data. That is NMI. Next one is in software interrupts. Software interrupts means there are some short programs are there. Okay, so these interrupt instruction can be used to test the working of various interrupt handlers. Okay, and this is a INT interrupt instruction with the type number INT2, INT0, INT1 like that. Okay, so there are totally 256 vectored interrupt. Vectored interrupt means it has some location. Okay, it has some memory locations. So that way you can call it as a vectored. Vector is nothing but it has a direction. Okay, that is the vector. So it has some location. 256 interrupt types are under this group. So they are actually type 0, 1, 2, 3, 4. It is categorized from type 0 to 256 only. Type 0 to 255. So totally 256 interrupts are there. They are type 0, type 1, 3, 2, 3, 4 have some particular functions. Then type 5 to 31, it is reserved for advanced microprocessors, and the 32 to 255 are available for both the hardware and the software interrupt. So type 0 means interrupt represents division by 0 situation. So division by 0 is not possible, right? So that is an interrupt. So it will execute the program like what it has to do at that time. If any program comes like 25 by 0, so that is a division by 0 situation. Next one is type 1. Type 1 is a single step execution during the debugging of a program. While you know about the bugging and debugging, right? While debugging a program, it has to execute a step by step. That is single step of execution. That is type 1 interrupt. Then type 2 is the NMI that we have already seen. Then type 3 is breakpoint interrupt. Type 4 is an overflow interrupt. So 0, 1, 2, 3, 4 having specified tasks. Then 5 to 31 will be reserved for advanced processors. 32 to type 255 are used for hardware as well as software interrupt. So, so these are the main interrupts of the 8086, right? So breakpoint interrupt, what is INT3? INT3 is nothing but here type 3, same is INT3, that is a breakpoint interrupt instruction. It is a 1 byte instruction having opcode is CCH. These instructions are inserted into the program so that when the processor reaches there, then it stops the normal execution of the program and follows the breakpoint procedure. So breakpoint, if you are giving some breakpoint address, once it is reaches that location, it will tell that this portion is over, so that interrupt will be comes in between. Okay, that is a breakpoint interrupt instruction. Then interrupt on overflow instruction. This is also a one byte instruction, that is INT0. It is a conditional instruction. It is active only when the overflow flag is set to 1 and branches to the interrupt handler whose interrupt type number is 4. And if the overflow flag is reset, the execution continues to the next instruction. So whenever the overflow flag is 1, the INT0 or the interrupt on overflow instruction, that is type 4 instruction interrupt will come if there is the overflow flag is set as 1. When the overflow flag is set as 1, whenever the data is exceed the system memory, then the overflow flag is set as 1. Okay, so whenever the overflow flag is set as 1, it gives an interrupt. So your answer is wrong. Okay, it is overflowed. Your answer is overflowed. So you have to stop your working, like that it will help, right? Then it will show some errors while doing in the computer program. Also, it is showing some errors, right? So that is what is the overflow interrupt. So once the overflow flag is reset, definitely it will move to the next point, next instruction. That is overflow instruction. This is what is about the interrupt. So what we have studied in today's class, the first point was nothing but features of 8086. The main thing is there is a 16-bit and 16-bit data bus and 20-bit address bus. That is the main feature of this one. Then totally 256 interrupts are there. Then we have seen the comparison between 85 and 86 as well. Then architecture of 86, we have seen it is a two functional unit. One is execution and second one is bus interface. So execution unit will control the whole process and it will give the instruction to the bus interface from where it has to fetch or decode the data, right? And bus interface unit, it will communicate to the peripheral devices as well as memory. This is what we have seen. Then we have seen about the pin diagram. So this is a 40-pin IC. So we have seen each pin in detail. That is what is pin diagram. Then next one, what we have seen, instruction. We have seen the interrupt. What is interrupt? What is ISR? Then what are the different types of interrupts are there? Hardware as well as software. Hardware, there are two types, NMI and INTR. And in the case of software interrupts, so there are totally 256 are there. So we can categorize it as 0, 1, 2, 3, 4 and 5 to 31. It will be used for advanced processors and 32 to type 255. And these are available for both hardware as well as software interrupts. So this is what we have seen today. So do you have any doubt regarding this?
Madam, there is no doubt, I seem so. Informally in the session, I'll just stop the call and then we'll have that.